today I am Autumn Kelly and I'm going to be presenting to you my extra credit project for Material Science 2001, which is on capacitors and specifically what they are and how they're made. Now, for many of us who aren't necessarily electrical engineers, I wanted to make sure to cover what is a capacitor and what they're used for. So capacitors store energy, and as you can imagine, that has many applications in the field of engineering. Capacitors, they are passive, so they cannot generate energy. What they do is they take an inflow of energy, then they store it, and then they can output that energy that is already stored in them, but it cannot generate any energy. Now, of course, these are an electrical component. They're used in many circuits and many electrical designs in cars, for example. So how does this happen? How do they store energy? This is to do with how electrons move. So because the current is caused by the flow of electrons when connected to a circuit, to an energy source, the electrons on one plate will move to try to pair with a proton. They'll be attracted to the protons, and they'll move and keep moving until one side of the capacitor is fully positive and one side is fully negative. And they're going to have an equal amount of positive and negative charge. This is how energy is stored, because then if the battery is taken away, for example, the current will flow again and want to get electrically neutral again. But notice, because of the dielectric, which I'm about to explain in the next slide, once the negative electrons get here, they cannot keep going. Okay, that is because the dielectric is an insulator. So what makes up a capacitor are two metal plates and then a dielectric material in the center that is an insulator. So two plates that are conductors, and then separated by some kind of material, whether it be air, whether it be paper or glass, that does not conduct. Something here that I want to talk about that's pretty neat is when I went to the Institute of Lafayette and toured there, they explained that they were actually studying dielectrics and specifically how silicon acts as a dielectric, which I think is very neat, because you can see that when we know what materials are made of, we can kind of understand better the science that is currently taking place in the world. And usually you would think that semiconductors wouldn't work very well as a dielectric, but they're using specifically silicon oxide, which has a larger band gap. Usually, also, when we use capacitors in our life, for school projects, for example, we're used to the kind of spherical capacitor, and those are ones that are usually coated in some kind of plastic casing. So we've got the metals, the two metal plates, the insulator material that separates the two metal plates, and then the casing is going to be some kind of other material, as well as the terminals. Okay, because we are material scientists and we're here to learn about materials, I wanted to go over how capacitors are made. But there are hundreds and hundreds of types of capacitors. There are complex ones, there are simple ones, and so I found what I thought was the most general process that is applicable to all of them. But this does mean that the specifics are ones that you would probably have to go research on your own after this presentation if you want to know more about that, and specifically a certain type of capacitor and how it's very specifically made. But as a whole, it starts with the metal being created for the capacitor, the cutting and forming of the metal. Then the electrode is formed and the dielectric is applied. Usually in the kind of capacitors that we see, the dielectric and the metals are wound together. This is a procedure that I shown. It's someone doing it by hand using a machine, but sometimes the process is also automated for, of course, the bigger production companies. And how they wind it together is they place the anode and then they wind the cathode around that. To continue the manufacturing process, sometimes the capacitor is impregnated with electrolyte, which I will explain later what that means specifically and why that's important, but that is not in every single type of capacitor, but that is in some. The terminals are attached so that they can be attached to a breadboard or to the circuit, and then this is a machine of the capacitor being sealed. Sometimes this is done with a thermoplastic seal, sometimes this is done with a hermetic seal. And the testing phase is very important for the process to make sure the capacitors are quality and are all the same. This can include things like aging, temperature cycling. This can include, of course, measuring the capacitance or measuring the voltage. So like I said, there are many kinds of capacitors, and I wanted to show this photo because I think it includes a lot of ones, including ones we don't see very much as students. I would say what we're typically used to seeing are paper ones if you've ever made a capacitor, and then of course the electrolytic ones are often used in labs and whatnot for school. The ceramic ones as well I've worked with before in school, but the other ones we maybe aren't as familiar with, so I wanted to show this. I'm going to go in depth more on specific types of capacitors that are more common. Of course, not everyone, but the common ones. So the most common, the most basic also type of capacitor are parallel plate capacitors. So these are kind of, as I described before, the most simple metal capacitor with a dielectric in the center. Now, what defines it being specifically a parallel plate capacitor is that it is uniform distance-wise apart, and the plates are facing each other. In addition, an electric field is formed by a parallel plate capacitor. Despite their simplicity though, these are used in modern electronics quite often, and you might, oh yes, and then the ones in the clean room are actually parallel plate capacitors, which is pretty cool. energy storage, signal filtering, and of course voltage regulation are all modern applications of parallel plate capacitors. Okay, I mentioned sometimes capacitors are impregnated with electrolyte. This is very important because this electrolyte allows a much thinner dielectric to take place. So it helps with repairing defects in the oxide layer, which means that these capacitors can maintain a much higher dielectric. These capacitors can have a much higher capacitance at a lower cost. Ceramic capacitors are non-polarized and they're very small and stable and cheaply made, usually. But that means because they are low in cost to create, they can be used everywhere. Our phones even have these in them. But ceramic capacitors are one that you can find very easily every step of the process on how to make them. For time and for the sake of this video, I'm not going to go in depth on each step in the process. However, if you want to look that up online, you can do so very easily. And I think the big important part is just seeing how the metal is grown to be specifically used for capacitors. Okay, last but certainly not least, I added foam capacitors. These are non-polarized, and these are specifically made with the electrodes being metal foil, and the dielectric being polyester, polystyrene, or polypropylene. These are often used in audio circuits and very high voltage applications, which means if you ever take a class in audio physics, you will probably have to work with these. Okay, that is my presentation, and thank you so much for listening, and I hope you learned something.